Let's welcome on stage Tomek from Adobe with his talk, or with his deep dive into cloud-native deployments with AEM and Kubernetes. Let's welcome Tomek.
Thank you very much. So my name is Tomek Rękawek. I work for Adobe. And in this talk, I would like to tell you about the cloud setup that we are working on. It's possible that you have already heard something about this. In this presentation, I won't be able to cover any dates or licensing details or prices, things like that. However, I will try to show you as much technical details as possible in 45 minutes, so I hope you will enjoy it. So the first two questions are what we are trying to achieve and why. So let's take a look on the current state of the AEM setup, AEM deployment. So I think that the current state is that AEM is like this tomato. It's beautiful and tasty, however, it requires a lot of care. We need to, I don't know, start. If we want to have an AEM instance, we need to start virtual machine, put the quick start there, prepare some scripts. Some of this is automated, but some of it's probably not. We need to push the content packages, push the bundles, start everything, hope that all the bundles are up. Otherwise, we just restart the instance, and maybe this time they will be up. And yeah, so it's like a lot of effort to actually start even a single instance. And what we are trying to do is to build machinery like this. It's a tomato harvester, and we are trying to build tools that will allow us to treat AEM as a resource, as a commodity, so that we can process instances at the massive scale, not focus on a single one, but just run operations on many of the instances. If some of the instances is down, that's fine. We can start another one and don't carry too much about this. Just have a tools that allows us to treat the whole thing as a large group. So apart from being able to run AEM at scale and scaling horizontally if it's needed with a single API call rather than a long work of cloning the virtual machine and so on, we want to have hassle-free deployments as well, like blue-green if the customer application supports it. And we don't want to we don't want to worry about the infrastructure. So we assume that the cloud provider like Azure or AWS should provide us with all the resources we need, and we don't really want to think about single virtual machines. We just want to be able to say to the cloud setup, okay, please start a few instances or 50 instances, and that will be it. And the cloud provider should take care of creating the virtual machines and running something on top of it. So that's the agenda for our talk, for my talk. So I will start with some quick recap on the AEM in Docker thing, and I will introduce some basic terms from the Kubernetes world, because the later slides will rely on those. We will have an architecture overview on the whole setup. We will spend quite some time discussing the publish persistence, because it's the most tricky part, I guess. And then we will talk about some auxiliary services and jobs that we have created to make the whole cloud setup smoother and working in a better way. We will see. So first of all, if we want to run things at scale, we need some kind of standardization. Because if every instance is different, we won't be able to treat them as a large group. I think it's quite obvious. If every box here is different, then we wouldn't be able to put them in such an efficient way on the ship. So these boxes are containers, as you probably noticed. So that's the answer what we are using here. We had actually a talk with Robert 2 years ago about the AEM in Docker. So if you are interested in this, just go to adaptTo 2017 page and you will find our talk there. I guess the main points worth noticing is that in Docker world we have a container which should include the whole application code, and we have some application state stored elsewhere. So we shouldn't really put the application state in the container, and we shouldn't really run any code from outside the container. So in our case, it's kind of different. It's kind of difficult because we have the content repository, and in content repository we have both application and state. So we have the apps and libs part in which we put the components, the JSPs, sometimes bundles, even in the install directory somewhere. But we also have the /content, /var, /etc, which is actually a state of our application. So if we want to somehow combine this with the Docker world, we had to split the repository into two parts. So in the Dockerized AEM, our repository is split into two parts. The first part, which lives inside the container, is the part containing the apps and libs and all the bundles. So the whole application AEM part and customer part, every application code basically lives in the container, while the whole state, like /content with our sites, /var with some jobs running and whatever, all of this lives outside of the container in a volume or in MongoDB, basically outside. This setup has a huge benefit because if we want to update our application to a newer version, all we had to do is to destroy the old container and start a new one from the newer image. And that's it, because the application code lives in the container, so it will be already the newer version, while the state lives safely outside, so it won't be destroyed in the process. Of course, it's not that simple as that in the practice, because there is a matter of content compatibility between versions, but yeah, that's the main thing. We are using feature model for our Docker image. So the feature model describes the AEM instance and also the customer external code. So all of this is grouped together into a single feature aggregate, and it started. So as a result, we have a ready-made Docker image that contains everything it needs. Once we start it, it should already run the whole application, the whole AEM, and all the custom bundles on all the custom code it needs, and there is no need to install anything in addition to this. Okay, so we have a beautiful Docker image, but if we use this Docker image, like if we have to, I don't know, SSH to virtual machine and run Docker run AEM just to start a container, it wouldn't make sense, because that's the whole point, that we can use it in somehow more clever way. So ideally, we would need a system that allows us to say something like this. Okay, system, please take this Docker image, please run it in 5 copies, in 5 containers. Please group all of these containers into a single load balancer, and please expose this load balancer under some public URL. So Kubernetes is exactly the system like that. Kubernetes allows us to start containers at scale. It has all the possible features regarding the inter-container connections, regarding the load balancing, regarding exposing the whole setup somewhere in public, and much, much more. But yeah, from our perspective, these are the most important things. So I wanted to say about 3 Kubernetes specific terms that I will use. So the first term is pod. So pod, it's like basic deployment unit. If I want to start Author instance from a container using Kubernetes, I will say to Kubernetes, okay, please create a pod that includes this Docker image. So pod, it's like the basic thing basic way to start things in Kubernetes. The other important things, I guess, is the service. Service allows to group a few pods under a single IP address, and so it's like internal load balancer. And this internal load balancer can be exposed to the world with an ingress that is basically a way to say, okay, this service should expose a path under this URL or under this domain. It's like reverse proxy kind of thing. So all of these entities, the way how they are configured is that in Kubernetes everything basically is represented by a YAML object. So if we want to create a pod, we have to prepare a YAML file, YAML descriptor of this pod, and send it to Kubernetes API. Similarly for the service, for the ingress, and so it's interesting that in Kubernetes we don't really send any commands to Kubernetes. We don't say to Kubernetes, okay, Kubernetes, please run this script, or please perform this, and this step. We only send a desired state, and Kubernetes takes care of preparing this state. So we are sending the desired pod configuration, the desired ingress configuration, and Kubernetes will take care of everything, of creating the new pod if it's required, of reconfiguring the ingress if it's needed, or leaving it as it is if it's not needed. It's also, it can be more complex like this. Like if we have more complex objects in Kubernetes, like there is something called deployment, and it allows to basically start pods with some images. If we update the deployment with a newer image version, then the deployment will say, okay, I need to somehow get to this state where we have newer image versions, so I will start the newer pods first. Once they are started and they are connected to load balancer, I can turn off the old pods. But if the new pods are not started for some reason, I will keep the old pods as they are. So it's like blue-green, but for free, basically just by updating the desired state. I think it's pretty cool. As I mentioned, we have a bunch of YAML files, YAML descriptors for everything, every part of the setup. Kubernetes itself doesn't offer any way to somehow manage this group of YAML files, but there is a Helm tool that allows to create something called chart. So chart is like a directory full of YAML files with some templating support. So we are using Helm to basically manage all our YAML files to keep them consistent and so on. Okay, so that was for the introduction about Docker and Kubernetes, and now let's take a look how we are using Kubernetes to actually start our deployment. So this graph presents the basic deployment that we have. So we have, as you can see, we have outer pods and publish pods. So these things are pretty obvious. We need to start containers, and they are living inside pods. The outer pods are exposed to some service, and the service is exposed as a ingress, so that if you enter outer.acme.com or whatever valid address, it will be directed to this ingress and then to this service and then to any of these pods, probably with some sticky session or whatever. So for the outer, we have decided to use MongoDB. In our case, it's the cloud offering from Mongo called Atlas. We wanted to have a cluster of outers so that every change is immediately visible on any given outer instance. So that was like the only option that we had. And for the publish, we are using segment store. I will spend a good bit of time in a few slides talking this, so I will just skip it for now. And we also are using something called Cloud Blob Store. I think it's available in the current version of AEM as well. It's like S3 data store or Azure Blob Store. So all our binaries are stored in the cloud as well, and this single blob store is shared by all the instances. So this allows us to have binary-less replication. And the replication itself is based on a message queue called Adobe Pipeline. So on Monday, there was already a presentation delivered by Timothy about Sling content distribution. So we are using it to basically replicate changes from outer to publish. Because of this, since we are using this pipeline, this message queue, we don't need to worry about endpoints of every publish instance. We don't need to use HTTP to somehow connect from given outer to publish instances and so on. We just replicate changes into the message queue, and the publish instances receives the changes from the message queue. What's cool with this message queue is that it's persisted. It's like Kafka, something like Kafka. So if some publish I don't know, loses connection to the message queue for some reason and then reconnects, it will just grab all the pending messages. We will use this feature as well in the publish persistence just in a second. Okay, so for the publish, we have decided to go with the segment store. The reason why is probably that it's faster. So for the outer, we needed clustering to be able to have multiple instances working at the same time, and they should exchange data between them. But for the publish, we don't really need to have this kind of synchronization between all the publish instances. We only need to have them the common state, and the only source of the changes on the publish should be the replication queue. So we have like many single publish instances, all taking changes from the message queue, the replication changes. So we don't need an extra layer of synchronization between publishers themselves. So this is faster because synchronization is always expensive and it would make it slower. However, we have to deal with a few issues. It's not for free. So first of all, if we start a new publish and we start new pods in Kubernetes very often, they can go down and up for whatever reason. So for this often event of starting a new publish pod, we need to somehow get its states, get its segment store from some place. because otherwise it would be outdated like by months or something. So the easiest way is to just copy existing segment store into the new instance, and that's how we started. There are two potential problems with it. The first problem is that copying files between pods is somehow tricky, because we would need to somehow expose the files so that they can be accessed, expose them in one publish and then access them in another. So it's like kind of tricky thing. And the other thing is that what we, for example, scale down the whole publish farm to 0 for some reason, or they just go down because of some problem, and then we want to get them up and where they should take their state. So I will talk about the solutions for two of these problems. The first problem with accessing the segments from one pod to another, it was solved by introducing something called Cloud Segment Store. So it's like a new plugin for the segment node store. Normally the segment node store stores its data in the segment store directory. So if you start a basic AEM instance and go to CRX quick start repository segment store, you will see a bunch of tar files. So what this new implementation does, it takes these tar files, and rather than storing them locally on disk, it stores them in cloud service in like S3 or Azure storage, something. So that's this way. It's not much slower, which is interesting because of the caching mechanism and some asynchronous writes that we have introduced. It's not much slower than a local disk-based solution, and it also allows for really easy access. So if we want to start a new publish, we can just take the bucket from the existing publish and just copy it. The existing publish doesn't have to know about this. Really, we can just access its segments and copy it to some other place. The nature of the segment node store allows us to do it. It's like a append-only database, so there is no. It's not dangerous. We don't risk like that we will get some incomplete state, because it's like append-only. So the worst thing we can get is slightly outdated repository if a new segment is already being written. And the solution for the other problem, like how should we choose the publish to take the content from, is this. So we have introduced a dedicated publish instance called Golden Publish. It's not connected to load balancer, so all it had to do is just to keep the main golden copy of the repository up to date. So when a new, to summarize this, when a new publish wants to start, it just takes the golden copy of the segment store, copies it to its own place, and then start on top of it. So that's the how it works, at least how it works for this stage. I will tell you about the evolution of this approach because it has some problems too. So this is the state we have. So we have the golden publish with some segments that it has written some time ago, and maybe this segment is being written right now. We have two publish instances that are quite old. When they have started, it was only 4 segments, so publish 1 and publish 2 copied these 4 segments to its own place. And we have also the publish 3 starting, which is in the process of copying, and after the publish 1 started, it worked for some time, so it had to write something. So it created its own private segments, not shared with anything else. So this approach works, but it's hard not to see that there is a lot of redundancy. So we have like 4 buckets, and like 75% of these buckets is duplicated. So it costs money to have this kind of redundancy, which is not really needed because, yeah. And the other thing is that cloning this redundant segment list, which is the same for every publish, cloning this may take some time, and it would be better, since we are starting publishers at scale and we do it often, it would be better to make it faster. So what if we can somehow reuse? What if this publish don't actually copy these segments, but somehow references them from the golden copy? And this publish similarly. And this one, it doesn't have to copy anything. It would just reference the first 4 segments. This one, all of them can ignore, but the first 4 they can just reference because it's living somewhere in the service anyway. So that's the optimization that leads to the really final state of the publish persistence. So the way how it works is that when a new publish starts, it lists all the segments that already exist and uses them. It ignores any further changes, because if it doesn't ignore, then we would need to have some kind of synchronization between golden publish and publish, so it will be too tricky. So we just treat the first existing segments as some kind of immutable state. If the new publish wants to write some segments on its own, it uses some local storage, and that's it. And the golden publish works as it had before. Yeah. So this is the current state. We are using just a single bucket, and yeah, and there is no redundancy. There is no need to copy anything, and still every publish has a separate repository. Just by accident, most of this repository is the same as for every other publish, but it's like a separate repository that it doesn't have to synchronize with anyone else. Okay, so the thing with segment node store is that it's append only. So as you can say, if it's append only, we need to compact it somehow. We need to perform the garbage collection from time to time, because otherwise it would just grow indefinitely. So segment node store supports something called online compaction, and this is how it works normally in AEM, at least since a few versions. However, with the cloud storage, the online compaction doesn't work very well, because it has to iterate over all the nodes existing, and iterating over the whole repository in the network with network latency is somehow slow. So we have another approach for this, and this is actually interesting because it allows us to solve some existing problems with new technologies. So we have decided to introduce something called out-of-band compaction. So the AEM instance itself doesn't have to compact anything really. The compaction is being done in a completely different container. How does it work? So we have this pod called publish farmer. It's like taking care of the whole publish farm, and if the publish farmer decides it's the time to compact the repository, like every 24 hours, the first thing it does, it downloads all the segments from the cloud to local disk. It will just get some state close to the most recent state. It will perform the compaction like locally, and then it will upload the segments, but not to the same bucket, but it will create a new bucket with the segments. Completely new, not referenced by any publish for this moment. So at this time we have this new revision, this new bucket of segments, and it's compacted, but it may be slightly outdated, because in the meantime, when the compaction process is in place, it may happen that the author decided to activate a page, and then this page will be only in the old revision, but not in the new one. But we don't care about this for now. We just switch all the publishes to the new revision. So we update the golden publish to use the new revision, and we update we basically destroy the old publishes and start the new ones, or it's in different order. We start the new ones and destroy the old ones. And what happened with this new page that has been activated in between? So when the new publish starts, it says, okay, I have applied the replication messages like 1, 2, and 3. However, in the message queue, I can see that there are pending replication messages 4 and 5. So I need to apply them as well before I'm reported as ready. So this is, and this way we have compacted repository, and the pending changes are applied as well. This is kind of interesting, and we are using the same pattern in different cases. Whenever we basically need to perform some out-of-band, out-of-CQ external job on the repository, we can use the same pattern. We can just create a new generation of the repository with some changes, and then we can switch the publishers to the new generation. And we don't need to care about some changes made in the meantime, because replication queue, which is persisted, takes care of that for us. Okay, so that's how the publish persistence work. Now I will talk about something called sidecar. So a single pod, it's called pod, not container, because it can actually include many containers. So it's, as a trivia, something that you can certainly shine among your friends. The symbol of Docker or container or image is a whale. So a group of whales is called pod. So like we have a pack of wolves, we have pod of whales. So that's why Kubernetes authors decided to call this deployment union a pod, because it can include many containers. So we can use this ability to run many containers in a single pod for a few things. If we have multiple containers in a single pod, then there are two nice features about this. First, all the containers share the same localhost interface, so we can do some TCP connections without actually touching the network interface to avoid latency. And second thing is that we can mount volumes, create a volume and mount it in a few containers at once. All the containers in a single pod runs on the same virtual machine, so they can access the same volume. So it's easy way to share some files between containers if it's needed. We are using these features quite heavily. So this is how the AEM pod look like. We have, of course, the AEM container in here. The AEM container it logs to some logs volume, but we also have the dispatcher container. And the dispatcher container can use the local host connection to request some pages from the AEM. On the other hand, if AEM wants to flush some page because it was activated, it can use localhost as well to flush the dispatcher. We don't need to take care of, creating a mapping between given dispatcher and given AEM, as it would be the case if we have separate pods for dispatcher and instance. We just use localhost for the whole network activity, which is much more simpler. Dispatcher also it logs to the logs volume, and it stores the actual cache in some different volume. So that's the standard like entities in the AEM setup. However, we can also add another containers from different world. Like we have Splunk agent over here, which basically read the AEM and dispatcher logs from the volume, and it can send it to some external service. So this way we have a Splunk integration for AEM and dispatcher. The AEM instance and AEM container doesn't have to know about this Splunk. It just writes it logs as it used to do, and the Splunk is like entirely added by the Kubernetes configuration. So we have also one more container over here. It's called warm-up sidecar, and it was introduced. As I said, it's normal in the Kubernetes to have a pod down and then go up again. During this process, the dispatcher cache lives in a non-volatile, well, in volatile file system, which means that it's being removed every time we restart, well, delete the pod and create a new one. So the dispatcher cache is basically empty when we start a pod, which is, well, not very good, because then when we start a new publish, the first requests it serves may be somehow slower, because it needs to, I don't know, rebuild some client libs, to rebuild some JSPs, to, I don't know, just warm up. So in order to avoid this slowness, we have introduced this warm-up sidecar, and when the AEM pod starts, it somehow intercepts the startup process, and it basically sends the requests to the dispatcher and AEM, well, to AEM via dispatcher, asking for the most popular paths. So for the publish, it will just request for the content, home, whatever, for the JS files and CSS files and so on. This way, both the dispatcher cache is filled and also the AEM itself is somehow warmed up before it's being added to the load balancer. Now, how does the warm-up sidecar know what are the most popular paths? Well, it connects to the same logs volume, and for most of the time, it basically analyzes the request log, trying to find the most popular paths. And it stores its state in some Redis pod living outside, and all the instances uses the same Redis, and this way we can use some like group knowledge, what are the most popular paths for this particular deployment. So it's interesting because this warm-up sidecar also, it doesn't have to be supported in any, this feature doesn't have to be supported by AEM or dispatcher in any way. So when we have created this warm-up sidecar, we just added it to the AEM pod, and that's it. And we didn't have to modify AEM or dispatcher in any way, and even without that, we have a nice new feature added. Yeah. So all the things that I have described until now, somehow all of them somehow happens automatically. So we are starting, we are telling the Kubernetes to start an AEM instance, but that's it. And from this point, it's like automatic process for starting AEM, for warming it up, for the compaction happens automatically. However, sometimes we need a way to interact with our deployment, to perform some tasks that are somehow too complex to be automatically, or that, yeah, I will just use a few examples. And jobs are a way to somehow implement this task that should be done from time to time manually by SRE or ops person or whatever. I will use two examples to make it more specific. So first example is the content migration. We have our AEM instance running in the cloud. However, we also have some legacy AEM instance based on quick start, and we would like to transfer the data from the old one to the new one. And there are too much data. There is too much data to use content packages. So we need to have some process to migrate these terabytes of binaries from the old instance to the new one. So with the migration, there is some issue. The issue is that migration requires like access to the source environment and access to the target environment. And it's kind of hard to have a way to, in this case, to access both customer and or the legacy environment and the cloud environment. First of all, we don't really want the customer or whatever owns the legacy instance to access the MongoDB used for cloud, the segment no store used for cloud. It should be somehow encapsulated, it should be secured, and no one really should touch it directly. On the other hand, the cloud doesn't really, shouldn't really be able to access the legacy instances because it can be deployed in hundred of different ways and so on. So the way how we can solve this is by using like the militarized zone. So we have this two-phase migration process, and in the first phase, and in between these phases, there is this demilitarized zone. It's basically a container, like a bucket, a S3 bucket or Azure storage container. And in the first phase, we are using the jar tool, like CRX2Oak, or yes, there is something more specific, but it's very similar to CRX2Oak, to read data from the legacy AEM instance and to upload everything, all the nodes, all the binaries to this staging container, staging bucket, somewhere in the cloud. This bucket can be owned by customer, it can be owned by us, whatever. It just needs to be there with some credentials. Once the whole content is already here, we can run the phase 2, which is actually a Kubernetes job. And this Kubernetes job basically reads all the data from the staging container and uses its own mechanism to apply it to the production repository in cloud. And this way, the access to the repository is still encapsulated with some Kubernetes-based things. We don't need to actually access it directly, but it gets job done. The other example of the job is the job required to handle new indexes. So indexes are tricky because indexes in Oak lives in the /Oak index, and it's like they belong to the application, but at the same time the indexing content is in the same subtree. So directly under /Oak index we have this list of index definitions which belongs to application, but the indexing data is also stored in the subtrees over there. So if we want to add a new index, it requires some extra treatment. So the way how we can work with this is with another extra job. This job is responsible for basically applying the new index definitions to the repository. How it works, it examines the new Docker image before this image is deployed to all the instances, And if it can see that the oak index part in this Docker image contains some definition that it's not present in the repository, it will just perform the out-of-band indexing of the whole content. Again, no AEM instance is used to do it. It's just external pod that takes care of it. And once the whole indexing is ready, it's being stored in the production repo. And then the whole deployment can carry on. The new Docker image is started, and it will use the new index. So there are other topics that I just want to mention here. The feature model and replication was covered already in this adaptTo conference. I haven't talked anything about monitoring, but we are using Prometheus and Grafana. It's like deserves a whole presentation itself. The other topic is the whole CI/CD pipeline to build the Docker images, the network policies that somehow takes care of, it's like internal firewall between pods. So I'm happy to talk about these things after the presentation, and because this is the end of this one. Do we have time for questions or not really?
Well, I think if there's one question over here, yeah.
Is the cloud segment store available in Jackrabbit Oak? And if it is, what are the available cloud provider implementations?
Yeah, it's available in Oak. Right now we have Azure implementation, so it's for the Azure storage. But it's possible also to implement the Amazon one in a very similar way.
Okay, sounds all good and exciting. The question is, like, the whole publishing part is quite complicated as it looks like, and a lot of new things have been created. So the question to me is just, in theory, it sounds like there could have been just a publish Mongo instance one, and then the whole replication maybe would have been easier because you only have one target and you also have scalability. Why didn't you choose that design?
Mm-hmm. Mongo document node store, which serves the Mongo, is slower than segment node store. So we would have to have more published pods to serve the same amount of traffic. So it's just a matter of cost, because if we use Mongo, then we would have the synchronization between publishers, but it would be at cost of the performance. And with this, we can still have all the publishers synchronized with the replication queue, but they are pretty fast because segment node store is faster. So I guess that was the reason.
Okay, thanks.
Okay, so thank you, Tomek.
Thank you very much.